Welcome to this presentation on adaptive and robust distribution system state estimator handling unknown noise statistics. This research was conducted by Sayantan Chatterjee et al. And published in 14th August 2025. Today, we'll explore the key findings and contributions of this important work. Let's begin by understanding a problem this research addresses. Good morning, everyone. Imagine a world where your electricity is always reliable, even as more and more homes generate their own power from solar panels. That's the future we're building, but it comes with a significant challenge. Our modern electricity grids, known as active distribution networks, are becoming incredibly complex. With the rise of distributed energy resources, like rooftop solar and local wind farms, the power flowing through our neighborhoods is constantly changing, making it very difficult to accurately monitor and control. Did you know that integrating these intermittent renewable sources can make our local power grid behave unpredictably, like a constantly shifting puzzle? This unpredictability can lead to inefficiencies or even worse, power outages. Our research tackles this fundamental problem. How do we get a clear, accurate, and real-time picture of our grid's health, even when it's constantly in flux and the data we receive might be noisy or unreliable? To understand our approach, let's use a simple analogy. Think of our power grid as a vast interconnected city, and our state estimator as a highly advanced GPS system trying to pinpoint the exact location and status of every vehicle and road at all times. Traditional GPS systems, like what we call the Kubacher-Kalman filter or CKF, work well on a clear, predictable highway. But our modern grid is more like a bustling city with constantly changing traffic, unexpected detours, and even some faulty road signs. First, to handle the constantly changing traffic from renewable energy sources, our system, called QSCKF, learns and adapts its predictions on the fly, much like a smart GPS that adjusts its route based on real-time traffic updates. But what if some of those road signs, our measurement sensors, are occasionally giving us completely wrong or noisy information? Our proposed solution, RQS-CKF, is like a super smart GPS that can spot these bad signals or outliers using a technique called Mahalanobis distance. It then intelligently decides to trust these suspicious signals less, effectively inflating their error margin without ignoring all data. It's a self-correcting GPS that ensures we always have the most accurate picture, even when the information is messy. So, how well does our self-correcting GPS perform? The results are really encouraging. We tested our RQS-CKF system on realistic power grids, including complex 1-3, NODE, and 1-2-3, NODE models with significant renewable energy integration. Our big win is that RQS-CKF consistently delivered superior accuracy in estimating the grid state, that's the voltage and phase angles at every point, compared to existing methods. Even when up to 60% of the measurement data was contaminated with unknown, non-Gaussian noise, meaning it was highly unreliable or faulty, RQS-CKF maintained its high performance. This means we can get a much clearer, more reliable picture of the grid's health, even under the most challenging conditions. And critically, it does this with only a minimal increase in computational time, about 1-to-1, 2% more than its adaptive predecessor, making it fast enough for real-time operation in today's dynamic power systems. Why are these results so important for our world today? Our research is a crucial step towards building a truly resilient and sustainable energy future. As we rapidly transition to renewable energy sources like solar and wind, our power grids must evolve to handle their inherent variability. This technology provides the smarter brain needed to integrate these green energies seamlessly and safely. By accurately monitoring the grid, we can prevent potential blackouts caused by sudden changes in power supply or demand. We can optimize the flow of electricity, reducing waste and making the grid more efficient. This isn't just about technology. It's about enabling a future where clean energy is reliably delivered to every home and business, supporting our global efforts to combat climate change and ensure energy security. It's about making our power grid not just smart, but truly intelligent and robust. So, what does this mean for you, the every user, in the next 5 years? Our research directly translates into tangible benefits for your daily life. First, you can expect fewer power outages and more reliable electricity, even during peak demand or unexpected weather events, because grid is better equipped to manage itself. Second, by making the grid more efficient and better at integrating cheaper renewable energy, there's potential for lower electricity bills over time. Third, this technology will enable a faster and smoother adoption of electric vehicles and smart home devices, as the underlying power infrastructure can handle these new demands without strain. Ultimately, this research helps accelerate our transition to a greener energy mix, powered by clean, sustainable sources, ensuring a more resilient and environmentally friendly future for everyone.